Welcome to qnawire.
Same radius of Earth, but it has a variable density of the planet. So here's my representation of that. It's densest at the middle, and then it gets less dense as we move away from the center of the planet. And then we're asked to find what the acceleration due to gravity would be on the surface. So the variable density doesn't actually really matter for that because we're looking outside of the center, outside of the planet itself. And because the density distribution is symmetric, we still know that the center of mass will be right at the middle of the planet. So we can just reduce this situation to a point particle with the mass of the planet, and then a distance r, maybe I'll just call the radius r. A distance r away, we want to know what the acceleration is at that point. So no difference. And so, as we've seen many times, we know that this acceleration is just going to be the gravitational constant times the mass of this point, and then divided by the distance squared. So we know the radius, it's the same as Earth, so we just need to find what this mass is. And so that's where the density distribution will come into play. But beyond that, it doesn't matter. If they had told us what this mass is, it doesn't matter at all that the density is variable. So how are we going to find this mass? So we can say that this mass is just going to be the density of the planet times the volume. But because the density is variable, that means we'll need to integrate, we'll need to write a differential volume term and then integrate over that full volume to find what the mass is. So we want to set this up like an integral of the density times a differential volume element, and then we're integrating over the full volume of the planet, and that'll give us the total mass. But fortunately, this density distribution is symmetric, so it's spherically symmetric and varies only linearly with r. And so that means we can actually set this up then as integrating spherical shells. So we're kind of drawing little spheres in here, and then we have r go outwards. So then we integrate these out to get the volume. And so that'll make this function a little bit easier. So rather than integrating over a full volume, we just integrate over the radius of the sphere. And so the surface area of one of these shells is just 4 pi r squared, so just the surface area of a sphere. We want to use little r here since this is a variable. We're doing an infinite number of these little shells. And then we still have our density, and then we integrate with respect to r. So this integral looks a little bit more doable. We just now need to find what this density rho is, then we can plug that in. So we're given the density at the center of the planet, so I'll call that rho naught. And then we're also given the density at the surface, so rho sub s. And so we want to find then what rho as a function of r is. Well, we're told that it's a linear density function. It increases linearly. So presumably then it takes the form of ax plus b. And I'll say ar since r is the variable we're using here. So we know this is going to look like ar plus b. So we just need to find what a and b are, and then we'll have our density function. So starting with the information they give us, they tell us that at the center of the planet, so where r is 0, we know that this should have the value of rho naught. And so that then, if we have r being 0, that's just going to equal b then, when we plug in r0 in this expression. So we found b. And now looking at the surface, we know then when r is capital R, we should have a capital R plus b, and then b we've already found is rho naught. And then we know that this should equal the value at the surface. So we can solve for a now, and we should get that's going to be rho sub s minus rho naught over r. And so plugging now in a and b into our expression here, we should get that this is rho sub s minus rho naught over r. and this whole term times little r. So this is the linearly increasing term. And then here is our constant b, so plus rho naught. So here is our density function. And so now we want to plug that in up into our integral, and then we'll be able to evaluate our integral and find the mass. So looking at this integral now, we will have 0 to r. So this is what our mass is going to be. 4 pi little r squared. This whole thing is multiplied by our density, so rho s minus rho naught over the radius. And then this is times r and plus rho naught. And we integrate this whole thing with respect to r. So we can pull out the 4 pi from this, and we can see it looks like then we have an r squared times an r for an r cubed. So m equals 4 pi. And so then this first term of the integral, we would have r cubed, so that should be r to the fourth over 4. And then times this constant here, so rho sub s minus rho naught over 4. And then this term, it would be multiplied by r squared, so we should then have r cubed over 3, and that's also times rho naught. And then we're evaluating this whole thing from 0 to r. So our mass then is 4 pi, and then we plug in r over here, so we'll have capital R to the fourth over 4, and then divided by r. So that then should be r to the third over 4 times rho s minus rho naught. And then we have plus just r to the third over 3 times rho naught. And then we can see when we plug in 0 for r, this whole term is just going to be 0. So we can simplify this with a little bit of algebra. So if we distribute out the 4 and then kind of group all of our like terms, we can get this to look like pi r cubed and then times rho naught over 3 plus rho s. So there's our expression. So we know the radius is just the radius of Earth, and we have rho naught and rho s. And so we can find then that the mass is 5.71 times 10 to the 24th kilograms. So they don't actually ask us for this value, but it's what we need to solve it. So there's kind of our main results. And then finally now we can take that mass and plug it in up into our expression for the acceleration on the surface of the planet. And we finally then get that that is 9.36 meters per second squared. And so there is our real answer.